Hi guys, welcome to our fifth video in chapter 16. This video is going to cover reaction spontaneity. So we've got two real objectives for this video. We want to be able to define a spontaneous and a non-spontaneous process. And then we also want to be able to explain how changes in entropy and something called free energy will determine if a reaction is spontaneous or not. Okay, as well as other processes like physical processes such as melting ice. So to begin, I think it will make the most sense to define a spontaneous process, right? A spontaneous process is any physical or chemical change that once begun will occur without outside intervention. Another way to think about this is it happens on its own. So these are things that just, we see them happening in nature and they naturally happen, right? Nobody makes it happen. An example that I like to use here is rusting. So if this is an iron chain, if we leave iron outside, over time, that iron will eventually rust. It will turn from iron metal into iron 3 oxide, which is that crumbly reddish type material. Now, I've actually written the chemical equation for that down below, the thermochemical equation. And that's this top reaction here, where it shows 4 irons, solid, will combine with 3 oxygen molecules, and that will form 2 formula units of iron 3 oxide, which is a solid. Delta H for this reaction is negative 16 point, I'm sorry, negative 1,625 kilojoules, which means this is an exothermic process, right? And we talked about in the last couple of videos, if we flip the reaction and we go the other way, going from rust to iron, we see that this delta H is in fact now positive, meaning this is an endothermic reaction. And this might lead us to think that all exothermic processes are going to be spontaneous. And that's actually not true, right? In this case, the reverse reaction where we go from rust into iron, that is not a spontaneous process, and it happens to be endothermic, right? We just leave a piece of rust out there. It's not just going to suddenly turn into iron. However, if we think about this picture here, when we have ice, we put an ice cube on a table, that ice cube is going to melt. That is a spontaneous process. It happens all on its own. However, it is also an endothermic process. In order to melt, ice must absorb energy. So that is an endothermic process. So clearly, it's something other than enthalpy that's determining whether or not a process is spontaneous and whether or not it'll actually happen, right? Here, this is an exothermic process. Here's an endothermic process. Both are spontaneous. And this leads me to one of our first major new topics for this unit or this video, and that is entropy, this idea of entropy. And here's the definition, right? Entropy, abbreviated S, is a measure of the number of possible ways that the energy in a system can be distributed. That's the textbook definition. I would consider entropy to be a measure of disorder. Okay. And so what entropy is a measure of how disordered a system is. And so I have that pictured in this video here, in this picture here. It says, what is entropy? Entropy is a measure of the disorder of a system or energy unavailable to do work. And I can actually, we can see in our example here, right? We have a solid going to a liquid, going to a gas, and this is example of increasing disorder. Our particles are very rigid and stuck in the solid, and they are very free and can move about as much as they want in a very disorganized way in a gas. Also notice these little annotations here that show us delta S when we go from a liquid to when we go from a solid to a liquid. Delta S is greater than 0, meaning that entropy has increased. And the opposite process going from a liquid to a solid, now delta S is less than 0, meaning that our entropy has decreased, okay? And so similar to enthalpy, the delta S of a system is going to be the entropy of our products minus the entropy of our reactants, or where we end minus where we start, right? This concept of entropy and entropy change, this is actually what's known as the second law of thermodynamics. And that law states that entropy in an isolated system will always increase. That is the second law of thermodynamics. That is actually the reason that heat flows from hot to cold, because it is increasing the entropy of the system being studied, right? The isolated system there. Now, when we're predicting the changes in enthalpy, right? We would consider, just like when we were doing enthalpy, we would have the entropy of the universe is equal to the entropy change of the universe is equal to the entropy change of our system plus the entropy change of our surroundings. So, and our delta S for any process would be the S of the products minus the S of the reactants, just like we have up above, okay? There are instances when we can just look at a system and we can predict whether or not entropy will increase or decrease, right? And so I actually have, I think, seven. I have five specific cases to talk about here that I want to go through. So first, this first one is showing us entropy changes associated with a change in state can be predicted. The more free the product, the more the entropy increases. So that means that when I am transitioning from a liquid to a gas, I am increasing my freedom of movement, my disorder, and so that will be a increase in randomness, right? I will increase delta S would be greater than 0. On the other hand, if I freeze that liquid and go to a solid, now we're getting less disordered. We're getting more and more organized. So in that case, delta S would be less than 0, which means decrease in randomness. Okay. Second case, whenever I'm dissolving a gas in a solvent, it will always result in a decrease in entropy. If you think about it, I go from a gas here into something that is aqueous or dissolved in the liquid state, so gas to liquid. So that should decrease my entropy, right? Dissolving gas decreases entropy. Third case, if there's no change in state, a process that have more gas particles as products than reactants will increase the entropy. So let me say more gas particles increase the entropy. And you're kind of hopefully seeing a little bit of a trend here. As we form more gases or liquids, we're getting more and more entropy. So in this case, I have 2 moles of a gas on this side, on my reactant side, and on my product side, I have 3 moles of gas. And so because I am producing an extra mole of gas by this reaction, my oxygen splits off and forms an O2, then I can predict that my delta S will be greater than 0. I will have an increase in entropy. Fourth case, there are exceptions, but when we're dissolving something, typically our entropy is going to increase. We go from a solid into a liquid, and that allows it to have greater freedom. Additionally, when we dissolve sodium chloride, we go from a tightly bound formula unit into 2 free-flowing ions that are aqueous. And so again, an increase in our entropy. There are exceptions, right? And I wrote it here. It says, when dissolving a substance that causes the solvent to organize, it may decrease the entropy. And that is a very specific case that we will talk about if it comes to it, but it's not something typical for a high school class that we talk about. And then the fifth case, the last one, is the increasing temperature always increases entropy, right? So if we increase the temperature, we will always increase the random motion of our particles, right? And so therefore the system, right? And so that is entropy. Now, this is, of course, entropy is, again, a measure of disorder, and we know that delta S of the universe is always going to be increasing, but that does not mean that every single process that happens will increase the randomness of our system. Like, for example, entropy will increase when a wall falls down, right? When a bunch of bricks go from being ordered in a wall to falling down into a pile of rubble, but we can come by and we can put in the energy to stack up those bricks back into a wall. So we can reverse some of these entropy losses, right? And actually, this comes down to my next and final section for this video here. I know I'm getting a little long, but and this title that I have here is called Entropy, Enthalpy, the Universe, and Free Energy. Okay, so I have this title, and we have talked about entropy, that is the measure of disorder, enthalpy, the measure of heat content in a system, and we've talked about the universe, right? That's everything, system and surroundings. So delta S must be greater than 0. So for all of our processes, our delta S of the universe will be positive. We will be getting more disordered somehow in our universe, all right? I wrote here, in general, the delta S of the universe is positive if the following conditions are met. For an exothermic reaction or for an entropy increase, okay? So again, if we have an exothermic reaction or an entropy increase, then we will have a delta S of the universe be positive. It will increase our disorder in our system, our entropy. All right. And before we go on, I do need to define this concept, this last concept for this video that's new. It is called free energy. And that is typically called Gibbs free energy. And it is down here, it is considered delta G of our system. So delta G of our system, and again, that's Gibbs free energy. It's that capital G. And so at standard temperature and pressure, we can express that free energy using this equation. Our free energy, which is the energy available to do work, is our delta H of our system, delta H naught of our system, minus T delta S, where T is our temperature. So you take the enthalpy change and you subtract off the product of the temperature times your change in entropy. All right. If delta G is positive, then this process is not spontaneous. If delta G is negative, then this process is spontaneous. And so we'll do some examples of this in class. Please remind me to go over this question because I will forget. So remind me to go over Gibbs free energy in class and show you how to answer some of these questions. But I did put a table together to help you kind of quickly decide whether or not something will be spontaneous. Okay. So if we consider a chemical reaction that's happening, if we have an exothermic reaction, a negative delta H, and that reaction increases the entropy of the system, maybe it forms gas products, that will always be spontaneous. On the other hand, if we have an endothermic process, and that process results in a decrease in entropy, a negative delta S, that process will never be spontaneous. Now, the tricky part comes when we have maybe an endothermic process that increases the entropy in our system, and so they work in opposite directions. Or if I have an exothermic process that decreases the entropy of my system. Again, it works in different directions. So in each of those cases, I'll need to use a calculation because the spontaneity will depend on the temperature. All right, guys, that's all I had for this video. Thank you for watching. I will see you in the next one.